Thanks, guys. Jim Vaz Night Band. Awesome. We're going to hear from them one more time after the panel and after John's closing remarks. But it's my privilege now to introduce our final panel. And I actually get to not be on it, which is awesome. And in particular, these are the guys who are actually doing the work and leading the way in the standards committee and in the industry, many of them. And they work with many more likewise doing that to advance concurrency and parallelism that all of us can use and benefit and write about. So that's a wonderful thing to be able to do. Let me introduce them. Pablo Halpern is, and you can see their bios up there, he's from Intel, participates heavily in SG1, so he's very familiar with the Silk language extensions that Intel has for concurrency and parallelism, task parallelism, with some other related work. And so he's a great source of information about should things be a language or a library, and participates in SG1, concurrency and parallelism, in the standards committee. Michael Wong is the chair of the Transactional Memory Group, SG5. He also has some official titles. He is the CEO of OpenMP, which you might have heard of, and an architect for them. Gor Nishanov is from Microsoft. He is, you might have seen his Await 2.0 talk this morning. I heard it was standing room only, which is awesome. And so resumable functions, including generalized coroutines and executors and those kinds of things, and how these things all fit together, are part of what interests him and that he's implementing a good chunk of at Microsoft. Jared Hobrock is from NVIDIA, and he is the parallelism TS editor. So if you've heard of the Parallel STL, that is the man, wave Jared, who has his fingers on the keyboard. Of course, we think we're telling him what to put into the TS. What actually goes in is up to Jared. It usually matches up really well. And so as we look to Parallel STL for parallel and vector execution, he's right in the center of things there, and also at NVIDIA with the Thrust library that many of you might have used as well. Artur Laksberg of Microsoft, he's the concurrency TS editor, and so all the concurrency stuff that's going in, maybe resumable functions and .then, whatever the committee agrees on, he's got his fingers on the keyboard of that, and works at Microsoft also, and works on libraries there, including Parallel Patterns Library, PPL, C++ AMP, which have fed into, along with NVIDIA, Thrust, and others, and Intel TBB, to the Parallel STL. And then Aid Miller is an author. He's got two great books out. In particular, his two latest, one on C++ AMP, one on parallel programming in general. So all of these have a wide expertise of parallelism and concurrency. So I'd like to just open it up, and I'll invite, we'll have a challenge. We'll see if we can get lots of questions from you by having short answers and short questions. But let me start off with this. Why is this important? Why are you caring about this in a nutshell? And what is the most important problem still to be solved? Any of you?
We all talk at once.
Well, there is a dining philosopher's joke here because there are 6 panelists and 3 mics.
I think the most important problem facing parallelism, at least, is to make the easy stuff easy. So basically making parallelism, at least I think it's easy already. I think the problem is sort of educating students about parallelism early, such that it's the sort of the first thing that they reach for in their toolbox when they are thinking about writing their program, rather than what for loop do I have to write to make my program work.
So I'll preface by saying, like everyone in this room, I love C++, and I want to keep C++ relevant. And I think one of the key in keeping it relevant is parallelism and concurrency. In my world, I see too often C++ become a driver language because you have to downgrade to some local language or some machine language to get access to all the gigaflops in your machine. In my talks, I've consistently tried to push that in order to access all the gigaflops in your machine, you need to be able to have the language support and or library support to get that. So I want to keep C++ relevant. That's why I'm working in this area.
And also to the question on why it is important. A program that runs on a single core and on a single vector lane and doesn't use a GPU utilizes roughly 1% or less of the machine compute resources. And we think that that's not good enough.
Now, let me drill on that. 1% of the machine's compute resources. You're talking about a desktop machine, obviously, here, right?
Yep. Not necessarily.
Right.
And so does this matter at all for, say, your favorite iPhone 6? No, it's not really one. But is it for your favorite smartphone? Do smartphones care about parallelism? Surely this isn't invading the whole mainstream.
No, it is. The smartphones actually have GPUs in them, and they have multiple cores in them. It turns out that if you can do a calculation in 1/10 of a second instead of 2/10 of a second by using both cores, you actually save battery power. It's counterintuitive, but going from a totally idle state to totally saturating the CPU and then back to idle is more efficient than going into half-saturated state for twice as long. So that's just the CPUs, and then they do have GPUs in them. So adding on to what the question of like one of the bigger challenges we face is the number of different kinds of parallel hardware that we have it's not quite stabilizing yet, and we're trying to work against this kind of moving target. So we have GPUs that share memory with their CPUs and don't share memory with their CPUs, and then we've got the CPU parallelism itself and vector parallelism, and trying to come up with a simple model. I echo Jared's remark that keeping the simple things simple is important, and our challenge in keeping things simple is that this landscape is actually pretty complicated.
Thank you. Now, I invite you to come up and queue up at the mics if you have questions. I thought I saw one or two people coming there. Yeah, let's take a question from this mic.
Well, on this slide, can you clarify parallelism versus concurrency? Because it's two separate TSs.
Anyone want to take that?
Well, I wish you had been at my talk on Monday and watched the video. Basically, concurrency is a program structure technique that has been around since before multi-core was a big thing. So you have consumer, producer, you've got UI threads, the idea of collaborating and cooperating tasks that communicate amongst each other. And that can be done even when you don't have parallel hardware. Parallelism is about exploiting the hardware. So one analogy from my talk on Monday was basketball is a concurrent game. It makes no sense with one player. You need at least 2 players and preferably 10 on the court in order to have a proper basketball game. But track and field, that's a parallel game. You can have 1 runner and use a stopwatch and see how they did. Or you could have 10 runners on separate lanes and they shouldn't interfere or collaborate with each other in any way. Maybe they'll look over their shoulder at the other guy, but that's as much interaction as you normally get. So parallelism is about minimizing interaction among tasks, whereas concurrency is about properly isolating separate ideas and having them pass messages amongst each other.
And as I like to say, concurrency is you've got 2 tasks that are running asynchronously. The point is they don't wait for each other, but they could be independent. Parallelism is when you're trying to use many cores to get the answer faster because you're chunking up parts of the same computation to run in parallel. That's another way of looking at it. Mike?
By the way, I really love that sports analogy.
Yeah. We have heard of sports. All right, next question, please.
You mentioned that there's complication because there's different sort of GPU architectures, and it seems like you're trying to fit a model, and it's hard to fit a model on many different designs that seem to still be sort of in flux. Should we wait until the hardware guys have settled their battle before we enforce a programming language on it?
So you're right that it's definitely hard to do this while we haven't really decided what parallel architectures are going to look like in 15 years from now. One thing we can do is say, well, all architectures are probably going to need to be able to sort numbers, right? So we can start at that sort of level of abstraction, right? A GPU or a CPU or an FPGA or whatever. There are these basic things that they can all sort of agree upon that they can do. As things sort of solidify at the lower levels, that's when we can start talking about, well, what does the lower level programming model look like to target all these things in the same way?
So in my talk, in my GPU programming talk, I actually I attended all the other GPU talks, and I actually did a pretty much one-to-one comparison between C++ AMP and OpenMP's GPU programming model. I want a high-level programming model, and there was an observation that you can see that every feature is almost it's beginning to converge. That there's the same feature on one side. You have tiles in C++ AMP. We have distribute teams in OpenMP. They actually do the same thing to service a certain level of architecture. I asked Herb, about putting something like that into the standard, and he commented to me that it's still a little early yet. We need more user experience, and we feel the same way. With the better user experience, the design is beginning to converge, and right now there is still a bit of fragmentation, no question about it. But you need to learn this stuff now, and you need to know it. It helps your program. So I think in a short amount of time, a reasonable amount of time, there will be convergence.
Yeah, so Jared's right in that there are things that we want to do on any architecture, like sorting. There are also a bunch of patterns that have been around for a long time. That's patterns, as in patterns, design patterns. And a lot of those are implementable on many of these different architectures. And I would urge you to think about things from a higher level of abstraction, because a lot of those things can transfer across different problems, right? So, you can think about tiles or blocks or teams in OpenMP. There is some sort of convergence going on there, and a lot of these patterns like, master worker or, pipelining are very common, and they've actually been around in parallel programming for quite a long time, even though things have been changing all that while. People were using pipelines, 20 years ago on vastly different hardware.
Yeah, I'd add one more thing. Working for a hardware company, if we do not come up with high-level software abstractions, the hardware people will create ridiculous things.
They're going to do that anyway.
And it's the hardware manufacturers who recognize it, but they have software people, which is important. Gor.
I want to inject in this talk about parallelism, asynchronous IO. So who here is doing asynchronous IO? Wonderful. So we need safe, zero overhead abstractions that allows doing asynchronous IO safely and efficiently. So just to inject into this parallelism talk.
And by the way, IO is a perfect example of concurrency.
And we had this issue for many, many years. I mean, I'm from initially OS division and Windows cluster. Anyway, so we switched to modern C++ 10 years ago. And for us, modern means C++ 98, because with RAII and some of the patterns of not using new and delete, essentially we eliminated a whole host of bugs as a class. But we still had bugs. And most of them were in concurrency and asynchrony. And that is the area that is sorely needed help in the standard and in the library. So,
thank you. Question here, please.
So attending Paul McKenney's session earlier in the week, he emphasized that you start losing performance unless the memory that you're accessing stays close to the compute core that you're using for any evaluation. So the question concerns me that in the future, number of cores is going up, and we're not in control over which core is running our computation, or even if the computation is running around between different cores. Are we going to get to a situation where we start wanting to allocate and manage cores like we allocate and manage memory? Will we want some kind of syntax core or library to handle this?
Machines now already have the ability to define affinity, to be able to set your computation, your thread close to a certain particular CPU cache, for instance. All that is actually available on almost every machine. What remains is something that allows you to do it in a uniform way. Whether that's desirable or not is still to be debated in the community. Some people want to do it automatically by algorithm. Other people want fine-grained control. We actually have a feature that allows you to do that. Not to say that it needs to be migrated to C++, but yes, to some extent, there is a certain amount of complexity in there in order to make things efficient. The point of some of these algorithms is that as long as you don't get off to the point of coherency, get outside of that, your computation will be very nice and fast. Once you get outside of that point of coherency, which for many people is the L2 cache, it can slow down. People have noticed that. That's why they do supply these things.
So I think, so you mentioned locality. Parallelism and locality, they're really just the tip of the iceberg of the problems that you run into when you start trying to target these sort of more exotic architectures. So I would also count among those distribution, right? You often want to distribute a big data structure across several different, distinct memories. Another one is heterogeneity, right? The processors that you're targeting don't even speak the same, instruction set. So, parallelism is just sort of, parallelism and concurrency, these are just sort of the first two problems, I think, that we're going to need to tackle moving into the future.
And just to add to this, one of the concepts that is hopefully coming soon into the concurrency TS is called the executors, which is an abstract concept that allows you to execute a unit of work on a particular executor. And one of those executors could be the one that is affinitized to a core or a NUMA node. So those things are definitely coming.
So let me push back a little or see how you react to this statement. So it's sometimes been said that the reason that you ask for things like max hardware concurrency, STD max underscore HW underscore concurrency, how many cores do I have? Or things like that is because you're writing your own scheduler. And to the extent that we need those knobs today, they're transitional because the schedulers aren't good enough yet, so we have to take over control ourselves. Isn't it true that we call set thread affinity way less now than we used to because the schedulers are better? So is this a temporary or a point-in-time effect? What's your opinion?
Yes, but there's still caveats. What do the users want? Certain communities want very fine-grained control. If you're doing a PhD in some national lab writing some supercomputer programs, you know how this stuff works. Other communities, consumers, may not care about that kind of knobs and tunes because sometimes they often hurt them. I don't know if that will ever go away, but yeah, you're right. In a sense, as the technology evolves, less of that begins to appear. But I think at some point, there's still always going to be some access to the underlying.
Good defaults.
So it's funny you mentioned hardware concurrency. So I primarily program GPUs. I have no idea what to consider the hardware concurrency of a GPU, right?
It's okay, you can implement that function to return 0.
Right, so
that's legal.
Right, so a GPU has 0 concurrency then in that case. We can't even really agree on what a core is, right? The various vendors, they define it in different ways, often for slideware, reasons of marketing. We don't even know what the knobs should be. Like maybe we could agree today what the knobs should be for an Intel-style CPU, but I don't think that would be a very durable thing to agree on moving into the future.
Thank you. And our next question, please.
So you headed into answering my question before I even got here, but you didn't get up there. So Pablo mentioned that the hardware designer is going to keep creating crazy things. One of the crazy things that's appeared in the smartphone space lately is this ARM big dot little thing, where the same chip has 4 or 8 cores on them, but some of them are big and fast, and some of them are small and low power. But they all execute the same instruction set. They all have access to the same memory. It's not like the CPU, GPU model. The same code can move back and forth. So then you go to Alistair's point of, okay, well, I can't just let my thread migrate over to a slow CPU just because it happened to be the next one that was available. So you've already started talking about, I think those knobs are going to have to be there. In applications where you're using a really dissimilar architecture like that, you don't have any choice.
So, panelists, is it only ARM that has big little cores, by the way? Any other platforms?
Oh, no. I mean, only the Xeon Phi was originally designed as a coprocessor, and although now you can get it as the processor in a machine, it's still pretty much going to be used mostly in a coprocessor connection. So you'll have your 4 or 8 big cores talking to the Phi and offloading stuff to it. So I think heterogeneity is here to stay for the short term at least. Maybe for the long term, make it even more diverse, might converge. I don't want to guess, but yes, it's not just ARM. And yeah, I think that these knobs and dials are the kind of things, schedulers can actually do a pretty good job, probably better than most programmers, at putting the right work on the right core, but they will get it wrong sometimes, and there'll always have to be a way of overriding it.
Right. So we also have different kinds of cores for certain different kinds of power PC chips. It's it's in fact the idea, the difficulties with NUMA programming has always existed in the high performance community. They wanted to pin things to certain cores, and then they also want to spread it out. They call that gather scatter in another context. So that's most of our design is actually based on that demand, and that's why we have that kind of things in our specifications.
Great. Please.
So I've seen some interesting designs for languages where it's all about having thousands of things running concurrently, and the way they make that work is by putting some restrictions on threads on what they can do. Well, not even, they call them threads or processes or whatever, depends on the language. Do you think that use case is served by C++ right now?
Not yet, but it will be.
Can you elaborate? It sounds like you have something in mind, and I don't know if it's
yes,
specifically your project or other things.
Right, so we have several proposals right now in the committee. One is to add user mode threads analogous to boost context with some layer on top, and another is stackless resumable functions, which you can have billions of them. And they're very cheap, they're lightweight. If you use a function, you can use the resumable function as well, but they're not as powerful as user mode threads. So you need to pick the right tool. Both of them, I think, are needed.
So you already have some of that today when you're programming GPUs with something like C++ AMP, right? There are things that you can do in your regular C++ code that you cannot do in your GPU code because you're just not allowed to. The data parallel model doesn't let you do that. And in some ways, that's exactly the sort of thing that these patterns are not preventing you doing, but they're suggesting you do not do, because for reasons of performance and programmer sanity, they're likely to make you unsuccessful. So I don't think that's necessarily a new concept. I think parallelism has had a number of sort of programming models that have either suggested you don't do things or actually prevented you from doing those things in order to make it easier to reason about the system.
I think it's important to distinguish between capabilities of, these more exotic threads or limitations that exist because the platform just isn't as mature as a C++ thread yet, right? So GPUs are getting more programmable. These limitations are going to go away, but some of these limitations are actually important to take advantage of. Things being able to say, this group of threads, they need to be able to synchronize really quickly to get their job done, and they need to be able to communicate together as a group. That's sort of going to be important going into the future, just for scalability and for reasons of locality, and I don't see that going away.
Okay. Question here.
My question is about std async. It seemed like a good idea at the time, and it's proven to be increasingly problematic. As the parallelism TS, concurrency TS, and all these other cool proposals move into the TS stage and are voted into CSP 17 or beyond, do you see SG1 potentially deprecating and removing std async in favor of these new mechanisms? Or will it just stick around forever to haunt us?
So we've tried that, and we failed. I think std async is there to stay. It's not going away anywhere, but we are introducing a replacement, which is executors, which will be more powerful and a lot more scalable, a lot more customizable as well.
Stefan, can I answer you in a question? How do you feel about bind?
I hate bind. It needs to be deprecated and removed.
Thank you.
But we have not yet tried to do so.
Thank you.
Also, I remember being with SG1. One of the reasons we didn't deprecate it was because there wasn't a replacement. Looks like we're getting closer to having a replacement, and then we can have that discussion again.
Sorry, just to finish the conversation, I love bind.
However, this is not the functional programming or functor panel, so Pablo.
So I feel like we might have gotten into
No. Pablo.
We might have gotten into a little bit of an inside discussion here about because Stefan certainly knows the
I don't know what you SG1 guys are doing all day.
But just to make it clear to the audience who might not have been, who isn't part of this discussion, there were at least two issues that have surfaced with async. One is that it creates a very special kind of future that's different from every other kind of future. even though it has the same type, and that's confusing. And the other is that it conflates the notion of the future, which represents a value in the future, with a handle to some task that you can wait on and decide when it's done. Async gives you only one handle that does both tasks, and sometimes you need to separate them. And that's one thing the executors definitely helps, because the executor is the handle to the task itself, and the future is the future. And so I think that'll be a better pattern to use in the future, and maybe async may fall out of favor, whether we deprecate it or not, who knows.
Now, when I said my last thing, was it the word functional that made you reach for a microphone?
I wanted to mention that boost ASIO with bind frequently in examples will become shorter than boost ASIO with lambdas. That's how it is related to async IO.
Excellent, thank you.
So despite the controversy over async, though, there is still a somewhat small camp that believes that async serves the purpose that it was designed for. So just to explain, these kinds of discussion comes up frequently at the standard level. Herb will know very much about that. Something seems like an overwhelmingly good idea, but there is a camp where you do have to sort of see where they come from, and some of the original design point was retained in async, and this is the reason why we can't really get rid of it. We have to basically get async 2, or which in this case is executors. So
Thanks.
So I'm hearing a couple of themes. One is that hardware is getting richer and more powerful and more diverse, cores and coprocessors and et cetera, and that the job of software is to use all of that hardware optimally. I'd like to hear from the panel, where are we in terms of tools that tell the software practitioner how much of the hardware he or she is using?
Not great. Debuggers, we need the ability to debug, even debugging GPU code. I know NVIDIA has some things. We have a tools interface. We need that. I can't even think about how to debug transactional memory even right now, because it seems to totally break the paradigm in order to look inside a transaction. There was a guy, I don't know, somebody came up to me and actually talked a little bit about that. We're going to need a lot more work in terms of making that area work so that it can work with the programming model.
So in general, how is concurrent or parallel debugging on CPUs or GPUs today compared to 2 years ago? Have we made progress in these last 2 years? And what do you see happening, say, in the next 2 or 3?
Well, yeah, I think we've made a lot of progress. I totally agree with Michael. We have a lot of work to do, but I think we can be pretty excited about the work we've done so far. One of the talks I went to this week was on the sanitizers, including thread sanitizers. It's great the way we can use tools like Clang to instrument code to make debugging easier, to make performance monitoring, checking for races. Things like races is like one of the big bugaboos of parallel programming. I would say that the two big ones in my experience are the data races, where two things try to access the same variable at the same time, and one of them is writing it, and not getting the parallelism that you expected out of the program because there's something about your algorithm or the synchronization in your program that's preventing it. And these tools are definitely getting better, and intrusive instrumentation, I think, is a great, at least in the short term, I think it's our best bet. And so I'm really excited about the sanitizer stuff. Any other the vendors and want to comment on the tools?
Well, I can say that concurrency and parallelism definitely introduce some very unique challenges. And in concurrency specifically, very often what happens is you hit a breakpoint and you have no idea how you got there. You look at the call stack and it's meaningless, completely meaningless. So we are definitely making some improvements in Visual Studio to address that. But we still have ways to go, absolutely.
So I debug a lot of concurrency stuff on machines that's 128,000 cores, threads, whatever you call them. So I use this thing called Total View, which actually does a really good job. But there's still technical problems there in that, if you stop at a thread, does it stop all the threads? Or does it just stop that particular one? If you stop all the other threads, that changes the whole tree, a tree of information, and now your bug might have disappeared. not an easy problem. They do a very good job of it, I think, and other people are certainly making progress. I agree with Pablo. I really, really want race detection because I think that's one of the most interesting issues that we need to be able to overcome.
Very good question on tools. Thank you. Next.
Hi. I've done a fair bit amount of work on DSPs, and one of the things that I am into C++ purely for speed, for no other reason than just giving me maximum performance on the hardware that I have. Now, on DSPs, I've always found that the compilers there are, in some cases, they're very nice. For instance, if you have a loop, then it will actually show you, well, okay, I'm going to try and schedule this loop in 3 cycles, but darn, I can't do that because I don't have this guarantee. Now, if you would only give me this guarantee, then I could maybe do it in 3 cycles, but now I'm going to have to do it in 4 cycles. Stuff like that is feedback that I'm desperately missing from using normal normal CPUs. And the second thing is that DSPs typically give me a much finer grained control on how the hardware is used. For instance, you can tell it which region of memory you want cached and which one you don't care about, right? Do you feel that we lack tools like this in the general computing world, and should we maybe address that more?
Can I ask you which DSP are you using?
This was a TI's, Texas Instruments.
I figured that, yeah. So Texas Instrument actually use OpenMP to design their DSP is just another form of accelerator in my world. We cover a little bit further than graphics. It's DSPs, whether it's FPGA DSPs or even packages that are flying around as co-processors in drones and things like that. I had a little joke the other day when I was talking about that. So it's still pretty vendor specific, I think, in terms of the ability to do that. I think that's what you're finding. I think that we need some sort of general API for these kinds of things. It's all really under accelerators, in my opinion.
Yeah, I mean, another example, for instance, is the restrict keyword that they give, which just guarantees that if you have a function with 2 pointers, that you can actually guarantee that those pointers are never going to be pointing to the same memory region, which is something that, yeah, a compiler can deduct on its own.
Then you'll love the proposal. I'm trying to push through the standard, which is restrict aliasing semantics for C++ to replace C99 restrict.
Right.
Did you say replace or adopt? I'm just kidding. Next question.
Can std thread be a bit more configurable to, say, set the stack space and that kind of thing?
Stump the panel.
Would you write a proposal for that?
Maybe.
That's right. I don't think it offers such APIs currently. You have to resort to platform-specific APIs, obviously.
Well, so here's a question then. How do you do it today? If you want to use a std thread, but you want to do that and you're working on a platform that allows you to specify, say, stack size, how do you do it today and keep your code as portable as possible?
Keep it.
Or ignore
No
the last
comment.
part about portability. Go ahead.
If def, and now concepts on plain functions so that I can select on which platform and then supply for every platform a version for the threading model. Yes, but please write a proposal. Or use resumable functions because then there is no stack issues. They are stackless.
So let me ask a specific question, and we have implementers here. To what extent does using the standard thread native handle help you? Can you use that? Is that a sufficient gateway to write reasonably portable code that then gets access to such things?
I was thinking about that. The native handle will give you access to that kind of things, but I haven't worked with it, so I really didn't want to make a comment.
Well, another thing which I wished std thread had was to create it in a suspended form so that we can have it ready, so that we can resume it without potentially incurring an exception.
So, we have an empty queue. Next here, please.
Yeah, hi. So I know that there's AMP and OpenMP and all these, and TBB and all these different parallel frameworks. But if I care about portability and I want to have something that is standardized, what is the time frame that I'm looking at? I mean, what can I expect when as a programmer?
Are you asking for parallelism or concurrency? Let's say parallelism?
Let's say parallelism.
Okay.
So hopefully by C++ 2017, we'll have a full suite of parallel algorithms to target at a sort of a high level, sort this stuff, reduce this stuff, scan this stuff, that sort of thing. That can be very portable among a broad set of architectures.
So much of the current proposal brings in parts of TBB, Microsoft's PPL, and Intel's parallel libraries, as well as through Silk, some parts of that. Since you mentioned OpenMP, I might as well make the way I view OpenMP is that even though I am the CEO, I try to take OpenMP a little ahead and use it as a sort of an experimental platform for something that's even more way out there, and eventually brings it back to C++. For instance, we have vector SIMD capability as a high-level language already. I think that might get into C++, might not. It could, but for us, our paramount mission is to serve 3 languages: C, C++, and Fortran. So as a result, we always have these kinds of weird pragma things.
So now the question was, how can we start using these things? The one thing I heard in the answer is, oh, C++ 2017. But we have a parallelism TS before that, and aren't some prototype implementations already becoming available today?
Yes, absolutely. Great question. In fact, several vendors already have prototype implementations available. They are not maybe production quality yet. You probably shouldn't be using them in a mission-critical application, but you can start experimenting and testing it and see how well it works. It's also a good opportunity for you to submit feedback and find bugs and report it back to the vendors.
In fact, I think the 2 of you are among the ones writing
Absolutely.
such. And where can people find them? Are they on GitHub? Are they?
So Microsoft implementation is on Codeplex. It's Parallel STL, codeplex.com. Go ahead and you can fork it and you can work on it. And I'll let Jared comment on
The others, there are at least 2 other, maybe 3 more implementations on GitHub with names that are difficult to remember. But if you get onto GitHub, search for Parallel for each, you should find them.
Please.
Might be a bit of implementation question, though. For quite some time now, leading compilers, they have auto-vectorization units and algorithms that help transform single instruction single data to single instruction multiple data. Yet all the parallel frameworks listed here, like even OpenMP and others, they are very much explicit. Does the committee or gurus here have any thoughts about giving guidelines and maybe thinking about introducing auto-parallelization units, and specifically instances under which, let's say, your usual for can be automatically converted to parallel for if compiler using escape analysis or otherwise detects that there are no dependencies?
So we've done a lot of that work, auto-parallelization, auto-vectorization. It's somewhat disappointing in the results. Let's start with auto-parallelization. The things that the compiler can actually see to parallelize is hurt by the opaqueness in some respect of C++. So it seems to only work very well at Fortran and C levels. C++ is very challenging. Let me just give you an example. An iterator. You can't even, because most of that is function calls, you can't really even tell if the loop is changing the latch or the gate. I mean, you can tell it that it isn't, and for the most part, you know it's an iterator, it won't. But optimizers can't make that gamble. So to allow that, we actually need something more in the language, maybe an attribute. I don't know what it is yet. I've been thinking about it. The great auto-vectorization debate is also somewhat difficult. As vectors become bigger and bigger, and I think 512, 1024 now, the instructions are very complex there. And the conditions for automatically vectorizing things require some very stringent things. If you think transactional memory requires things to be transaction safe, auto-vector is almost as bad, right? You can't actually vectorize things only under very fairly strict conditions. So that too does not look like, and I still could be wrong, of course, because we've been working on this for about 10 years. So it's a difficult problem. Okay.
So auto-vectorization, despite those, has actually been somewhat successful. Auto-parallelization has been pretty close to a complete failure. So distributing among many cores has not worked well for a number of reasons. But now, that sort of the restrict idea that Michael was talking about earlier would help with both things quite a lot. One thing that allows auto-vectorization to go forward better than auto-parallelization is that the as-if rule of the language that says we don't care how the underlying instructions do the job, just so long as the observable result is what the standard says it's supposed to be, gives the auto-vectorizer some latitude. One of the things that makes it difficult for auto-parallelization is if you're actually running on different threads, it's totally observable. So, one of the things that we hope to do is introduce the notion of an execution agent that is something a little vaguer and a little bit less easier to pin down than a thread, but is nevertheless a separate thing that can run in parallel with other execution agents, and that might help with auto-parallelization. The other thing is that what you're doing with parallelisation, whether it's vector parallel or multi-core or GPU kind of parallelism, is semantically what you're really saying is these things are independent and can run in parallel. And ideally, you give the scheduler or the compiler the leeway to say that could run in parallel, but that wouldn't be profitable to run simultaneously, so we're going to just run it on one lane or one CPU. So in a sense, if you just identify the parts that can be in parallel, you can let the quote-unquote auto-parallelizer take over from there because you've given it the information. These things are independent. And that's the key piece of information that's necessary that C and C++ are so bad at because of all the aliasing issues.
So if I could maybe try to restate, and would this be accurate? Because you mentioned the as-if rule, which is our justification to optimize, and then you talk about declaring intent. So would it be fair to say that auto-vectorization is yet another optimization you can do, but it is not a substitute for declaring your intent and expressing a parallel program?
All companies, Intel has it, we have it. We have all these keywords that tells you that these things are independent or whatever. We haven't transferred that to C++ yet because we're not really sure how to put that forward. A question like that really puts a light on that demand. If there is demand, then we definitely will think of some mechanism of doing that, I think.
Thank you. Next question.
So this kind of answers partially my question was going to be that side effects are very, very big problems in parallelism, and C++ doesn't seem to have much way to annotate side effects at all. And it was wondering if there's any proposition or work in the way to allow like a more granular definition of what side effects you might have in a function.
So in the world of side effects, there's this thing called pure function. GCC has it, okay? When I was trying to do transactional, while I'm trying to do transactional memory, we were trying to think, we had this transaction safe function, annotated function, which says that this function doesn't have volatiles, don't have any assembler statement, and don't transitively call other transaction unsafe statements. We were trying to think of a way to expand that into a kind of a pure function to some extent, because that would sort of give the language a less transaction-specific coverage, which is what Biana asked us for, because now it's good for the whole language. In short, I don't have an answer yet in that respect.
So the closest thing to that, what you have in C++ today is const. You can say that this function is const, therefore it shouldn't modify an object, right? It should modify the data pointer that things point to. Unfortunately, there are two problems with const in C++. First is that const can be easily overridden by the programmer. You can always cast it away. And so the compiler cannot really trust that when making parallelization decisions. And also const in C++ is not deep, right? You have to think about not only the data that the pointer points to, right, but kind of the pointer itself and all the transitive closure of data that you can reach through that const pointer. And that depth is definitely lacking in C++.
Just before we take our next question, a speed round. In a sense in Siege, Age, you're teaching, we're all teaching, many of you are implementing these things. What is the top issue that users are facing today that you think needs to be solved next? Maybe it's something that was already mentioned.
For me, it's heterogeneity. I've got this huge code base of C++, I can't use them because it's not annotated the right way to work with the hardware that I want to program. This is a gigantic problem. I can't go and mark up all those functions just to be able to compile them for the GPU I want to use. I don't know the right way to solve it, but it's the problem I deal with the most.
To me, it's giving our users tools to write portable parallel code, something that doesn't need to use ifdefs.
Portable, efficient, asynchronous IO code.
I think for me, it's teaching them how to write code that allows them to be confident and reason about any side effects that one piece of code might have on another. C++ kind of doesn't have a lot that helps you there, so you really have to know what you're doing as a programmer.
Yeah, I was going to say pretty much the same thing, education.
So there's the part that I like to work on, and what I think is the users have in terms of. I think we still have problems in terms of knowing how to break down tasks and break it down into chunks that's workable. I think you're gonna if you start getting some of these and I'm actually sitting next to the author of the task region proposal, you're gonna find it not that easy to break things down into manageable tasks that doesn't break your cache line or overfill memory or things like that. We think that that's gonna come up next. But for me, I'm actually, of course, as transactional memory, I can't help but mention that I foresee a problem in the future where generic programming can't move forward because locks can't exist in generic programming. And that's what I'm trying to solve with transactional memory.
Thank you. Next question.
Hi. So I'm from the domain of scientific computing, so high-performance computing. I fight the fight every day of trying to push forward C++ in a deeply rooted Fortran world. One of the talks is in our center is can we substitute some of the code of Fortran, not all because there's too much code around, with C++. We are trying to, but we keep having a question back. Now Fortran can do this thing called co-arrays. I don't want to put you all in the tough spot because I really, really appreciate all the work you're doing. But has anybody looked into this? Because it is supposed to make parallelism a bit easier. It is we showed with Fortran code that it brings a great improvement in efficiency. So
Co-arrays and other Fortran idioms?
So being one of the few people who will just barely admit that I know the F word. Not enough to get me into working in it, but yes and no. We don't have anything like co-array. Co-array is a form of partition global address space. What that means is that it has an affinity. Certain address space has a better affinity to some CPUs, and it lays it out in such a way so that your array automatically addresses these different affinity segments progressively. So you don't have to do anything tricky. You just get it almost for free. We implemented in the IBM Fortran compiler, of course. No, we don't have something very similar to that because in order to have that, we have to have some sort of partition global address space model where you can actually address affinity closely. Maybe that's necessary, and obviously this is something that requires a proposal. I'm going to fall back to that.
I saw a couple of other panelists nodding in agreement. Anything to add? All right. Next question.
In GPU programming, often transferring data back and forth from the host to the device will kill any parallel performance you gain out of the accelerator. Is the parallel or concurrency TS planning on having a series of algorithms where you can transfer stuff to the GPU, leave it there, and keep running algorithms on it, and then get back a result? Because everything I've seen thus far says transfer it back and forth every time you sort or...
So the parallelism TS is completely agnostic to that sort of thing, but you can achieve what you're talking about just by having the right kind of allocator to allocate your memory on the GPU, stick that into your container, run your algorithms, and you can be confident that no data motion is going to happen under the covers. Moving forward, I think it's clear that having support for a single sort of unified address space is going to be really important because how many programmers are going to be willing to do what I just said? Probably not very many.
just going to add one thing, which is that, yes, you're absolutely right. Memory model for GPU programming is actually the most important and the most interesting and the most fun to work on in that respect, which is basically memory movement.
Yeah, I think one of the challenges we have in trying to come up with a really clean programming model for any kind of parallelism is how non-abstract a lot of these concepts are. You know, you have to actually think about the GPU's memory and the CPU's memory and the big cores and the little cores. And, you know, we can make one little inroad with things like allocators, like I think it was Alistair mentioned. Are we going to have to allocate our cores the way we allocate a memory? Maybe, but it still feels a little bit like a workaround for the fact that the hardware is so unabstract. Even the fact that we're working with cache machines, you know, all modern CPUs have multiple levels of cache, and if you're not aware of them, you can write something that really destroys your cache performance. It can make a couple of orders of magnitude difference in performance, but it's not abstract at all. You have to be understanding what's happening at the machine level, and I don't know of a programming model that abstracts that away. I know of programming models that allow you to ignore it to some degree, but not completely abstract it away.
So right now it's very, very explicit. You know, C++ AMP has cons, memory movement, and discard. We have target map to map from, map to from. You get the picture, right? It's pretty explicit. So you really got to know. Underneath, all the models promise that there's no excessive copies. We try very hard for it because we know that that's bad. Whether it's going to be done implicitly, well, that's kind of the thing that Herb is talking about, I think.
Yes, please.
I just want to, this is about parallelism, and there are, programs don't exist on their own. Most of the programs just are executed on some operating system. And many operating systems have this concept, variously known as jails or sandboxes or containers. Is there any move towards getting language constructs to support that model, that sort of parallelism model?
I need a little more clarification. Are you asking something like a Java sandbox type where it's protected from all the other?
That is correct. There's something called, in Linux, it's called container. There's a library called Docker that does that. On AIX, it's called the jail or something.
Yeah, the jail mode. We have this thing called the jail mode.
Yeah, so my question is about if there's a language construct that can help us programmers to think about structuring our program so that you have these tasks, you have separated them out, and you want them to execute parallelly.
So, I mean, people have been doing this for a while in that that's what message passing models of parallelism tend to give you, right? Largely because they were written for running across multi-processor machines, you know, in a large cluster. There are people that will say, well, you know, that's the model we should all use because it allows you to be very tightly aware of, you know, where data is consumed and there are no side effects because anytime I want to pass something, I have to send it as a message from A to B, and I can't circumvent that by, you know, passing a reference to a pointer to something that's on B. That just doesn't work. But again, this comes back to this. So this comes back to two things. It comes back to my concern that programmers need to reason about all these side effects. So from that aspect, it's good. It forces you to reason about all those aspects, but it's also bad because now you're back in this explicit copy world, effectively, right? Where every time I want to send something from A to B, I explicitly have to send it. I'm not aware of anything in the C++ space that explicitly does this.
We've been on parallelism for a while. It's hopefully I have a concurrency kind of question. I'm curious about .then and not just Visual Studio, but kind of how is that being received? What's its future? Is it going to appear in a TS? And then does it look like it has smooth sailing through the overall committee for 2017? And when might you be able to see it on other compilers, and also all the stuff related to .then.
Sorry, when you said .then, what's its future? I just cracked that.
Wow, pun not intended.
.then is currently part of the Concurrency TS. It has been pretty well received. It's moving forward pretty well. So if you're looking for an implementation, then in Visual C++, we have a library called PPL, Parallel Patterns Library, with a concept task and a continuation, which is very, very similar to what we have proposed to Future.
Mm-hmm.
But I also think that what we are proposing for the standard is actually better than PPL because we've learned from some of the mistakes and we've improved that. Boost Future is another implementation of futures with continuations. I definitely take a look at that.
Boost Futures, that's available now then?
It's available now from 154, 155.
What about without Boost?
Without Boost, I think that PPL is probably the closest that you can get to a mainstream implementation. Anybody cares to correct me?
I'd like to get it on one of these.
And one thing I'd like to bring out is that, so Gor, you gave a talk on await, and so resumable functions and await had been, until about a year ago, and for the first couple of years of standardization proposals, had been tied to .then. They were a syntactic sugar, but a major sugar, over .then. Is that still the case? Are those two still coupled?
No, stackful resumable functions are completely decoupled and it can be used to hook up to arbitrary asynchronous frameworks. Moreover, potentially, I think stackless resumable functions may lessen the need for .then in scenarios where expressing your state machine in a procedural manner is sufficient to handle your application.
Well, then I wonder, would the committee go, well, we have stateless resumable functions, why do we want to specify .then and have a redundant thing? Would there something like that develop, a tension like that develop, perhaps?
Well, there are problems where stackless resumable functions may not be appropriate. So
there are two tools that overlap.
Okay. And then Artur was mentioning executors, and it's unclear to me how that fits in with all that.
So executors is a very simple concept that allows you to take a callable object and say, hey, I don't know what that executor is and how it executes things, but go and do this work, right? And particularly one good example where executors can be used with futures is you can put an executor as a parameter to .then and tell the system, there is a continuation that I want you to run after this task or future completes, and this is how I want you to execute that continuation. Please run it on this executor.
Okay, thank you.
Yes, please.
I was wondering if I have not heard much mention of distribution until the person just in front of me, but like in Pablo's task idea, for example, I work in distributed computing where I have terabytes of data and huge numbers of machines running. If we have a task sub-feature, is serialization being taken into account in the proposals for the new parallelization so that we can also send things between machines, not just run them on one machine?
So other than being aware that it's an issue, I have not seen a standardization effort around distributed computing, separate memory space kind of computing. I think there will be more and more pressure to do so. What we need is a little bit more expertise in that area. Most of the parallelism expertise in the committee is a handful of people who deal with shared memory, either shared memory concurrency, or shared memory parallelism or a GPU parallelism. And the distributed kind of cluster sort of parallelism is not well represented, although there are people who know some things about it. Nothing gets done in the standardization effort without a proposal, and something that big requires a series of proposals and people to follow up and write the next version after it's been discussed. But it's going to have to happen because there's a limit to how much you can do with a single machine with a single address space, and we're going to need to have serialization and the message thing clean. And I think MPI shows us some good things and some good ways and some bad ways we can do that, and we should learn from that.
And I think that if Bjarne were here on this panel, he would also chime in about how C++ from the beginning was used with the concurrency library and for distributed and concurrent programming, because he worked for a telco. And so that was a primary domain. So I know he in particular is also very interested in seeing distributed memory and distributed storage continue to progress.
And there are a couple of proposals which are on the way to serialization, namely static reflection. The motivation, essentially, one of the motivation examples for static reflection is serialization. So when we get those proposals voted in, we can start building up on those.
We have a whole SG for that, and the chair is in the room somewhere with a camera. Excellent. Next question, please.
So I can easily reason about one thing happening at a time. When two things happen at a time, I generally need a little bit of help, either from my coworkers in the code or from tool support. I know now that locks are somewhat standardized. Is what they guard ever going to be standardized? Is there going to be standard annotations to tell me, hey, this lock guards these variables? Or am I going to rely on different tool chains to process this information differently?
Sounds like an interesting idea. I have not seen any proposals in that direction, but it does sound like an interesting idea to find a standardized way to annotate this variable is protected by this lock. It doesn't always work. Sometimes there are certain lock patterns that extend beyond that. But it's a very common pattern to have a lock guard a specific set of variables, and having a tool being able to trace through it and say, hey, you're accessing this variable without holding that lock, or or whatever, would be nice. I haven't seen any proposals in that direction. It would be something that certainly could be done outside of a standard effort, and then if it was really successful, could be considered for standardization.
Okay, thanks.
Empty queue. Next question.
In my experience in legacy code bases or with programmers who are new to parallelism, they don't know how to lay out their data. They don't know how to essentially expose the parallelism of their problem. Is there something that either the language or maybe the standard library could do to assist people into that way of thinking?
I think this is probably more of an educational issue, right? And how do you approach this problem? I would say profile your program first, find the hotspot, right? And if that hotspot happens to be a loop, that's a good candidate for parallelization. And that would be probably the majority of cases. Other scenarios are obviously more complex. But there isn't a silver bullet to this problem yet.
Can I add to this question? Is there a book you could recommend to actually learn about that? A single book, or two maybe.
So this is exactly the kind of problem I was referring to. I think the next big thing you're going to start meeting, now that you've got all these great tools and language, is exactly the top 10 problems of parallelism. Task decomposition is exactly what that is all about. And I don't know why you're asking me, but I read a lot of books, so for me, when I look at things like parallel decomposition, there are certainly pattern books. I myself read this book by Maurice Herlihy called the multiprocessor, not C++, but multiprocessor programming. It's like a huge textbook, really, and I find it seems to cover a large amount of time. I don't know if I can't really say for sure whether it's in there or not myself.
So it's a shameless plug, but the parallel programming book in C++ is actually available for free online on MSDN. I'm not saying it's the best book, but it'll get you started, and you can read it for free, and it covers a lot of the sort of basics that will get you out of these sort of obvious pitfalls.
So how do we encourage professors or other educators to actually educate people in this? Actually is even more along that question.
I think they're ahead of us, to tell you the truth. I don't know of a computer science department in any university that has a significant computer science department that does not have parallel programming as like a second-year course or something like that. I mean, they know it's hot. They know it's important. They could use better tools. but they do the best with what they got.
Jumping back to the previous question about how do you associate data with locks, I wrote an article about that myself. I'm not on the panel, but I'll just say, and here's a quick idea, and it talks about how to basically just encapsulate a structure where the private data and a mutex go together, have accessors, and if you implement lock, unlock, and such, it's actually lockable. You can use it with a lock guard. There's more details about how to regularize this pattern, but if you just Google for my name and associate data with locks, you should find it. Next question.
Being.
I believe yesterday we had a keynote speech that data-oriented programming that made the point that if we want performance, we pretty much have to do away with all the abstraction and drop down to, arrays of flows, pretty much. And now, if we add parallelism to this, we enter a whole new world of, completely non-abstract, very specific hardware that we need to target. And yet the standard is, the efforts in improving the standards are focused on making more abstract solutions. So do you think, actually, how do you reconcile those two things? Do we need to go into the more abstract direction or actually get down into the specific hardware solutions?
Well, I would argue that we need to go in more abstract directions if we care about portability. If we care about absolute peak performance, no library is going to help you there, right? You're going to have to be responsible for all the code yourself. At least that's been my experience.
I think it is a tension that we deal with in C++ all the time. C++ is intended to have minimal penalty for abstraction, and we keep trying to stretch that envelope. So the ideal within the community is always looking for how can I make this abstract? And sometimes that doesn't serve us, and it's true. Sometimes you need to expose something that causes your abstraction to leak more than you would like. But that is definitely continues to be the direction that the standardization is looking at. I think that we actually don't really have much of a job if we don't try and do that. The vendors will just sort of tell you, this is the system call you make to do this thing, and you'll end up with the Wild West. I think that the constructs, in order to work on more than one piece of hardware and one operating system, are going to have some level of abstraction. And the trick is to find the balance of having that abstraction without getting in the way of optimal performance.
Yeah, so I'd just like to add to that. I mean, I think that the two things are somewhat orthogonal, right? If you want portability, you have to add some level of abstraction, and if you want raw performance, you want that all out of the way. I think we already talked about this with thread. You can get from std thread to native pointer. So you can maintain that level of abstraction, but if you want to sort of circumvent it and get down to the metal and write something that's less portable but more performant, you can do it. And I think the STL, for instance, has lots of places where you can see examples of that. And I think that's really your only recourse. It allows people who maybe care about slightly less about performance but more about programmer productivity to use the abstract approach, and people who really, really care about performance, and if you're in the high-performance computing space, you really, really care about performance, to go down to the level that they're comfortable with.
Alex Stepanov had a very great advice on how to discover the abstractions. You don't start with abstractions. You start with the best way to solve a particular problem on a given hardware. And then you're trying to see, can you discover something that can raise the level of abstraction? And only then you can actually arrive at an abstraction that can be useful and efficient. So if you just start with an abstraction and hope it'll go with
So is that
wonderful
the way?
performance. Yep.
Is that
Well
the way
said.
that the committee works? They start up from the bottom and go up?
Oh, that may be how individual proposals work. The committee works by evaluating proposals.
Oh yeah, sure.
Yes. Nice answer. Thank you. Next, please.
So, having recently started using C++11 just because of constraints on projects that I've worked on, I find that I was very excited about the support for some of the models like thread, and I thought bind might be kind of cool, and I thought function might be really nice abstraction. But I found while trying to create portable code, a lot of that precluded, it encouraged you to program in a specific model. And that is, hey, I got a thread, I need to do something else somewhere else, I'm going to park my thread and just let the kernel handle scheduling. Having spent a large amount of time on a large vendor's operating system, some people might know who that is, there's a different programming model that, you know, Cutler versus Torvalds and BSD and whatnot uses that allows for you to gain efficiency if you cut your program into the right types of pieces. What I was a little disappointed with C++11 was the decidedly, now keep in mind this is my opinion, Linux flavor or that style or model of threading. Now I realize that gets down to the kernel level and how the kernel handles scheduling.
Is there a question for the panel?
Yes, there is. I wanted to give you a preface of what the question was, or what I was getting to. What do you, I mean, I think the stateless functions or resumable functions might come in handy there, but what do you do to encourage a better programming model from the get-go when you start using the standard functions? Because if you start going down the route of using the standard functions, it definitely encourages a specific style of programming, which makes it more difficult to adapt to other styles of programming, which may be more efficient in the long run.
So what kinds of things help people, give them guidelines and guardrails to write good parallel programs?
Well, I'm not sure if I'm going to answer that question the way you rephrased it, but I think what I can definitely say about C++11 is that it was about threads and mutexes. The concurrency stuff that was put in there was the base level stuff we've had for a long time, but was never standardized into the language, and everybody had to do it differently on their own operating systems. We recognize that. The reason why we have a separate working group now on concurrency and parallelism is to move beyond that. So what's in C++11 definitely is what you said. It's not about tasks, it's about threads. But thinking about tasks is the next step, and both the concurrency and parallelism things that we're doing in the standard are working in that direction. So executors are about tasks, the parallel algorithms are about tasks, the parallel fork join proposals are about tasks. So it's really kind of the next stage. It's not like I think there's something wrong with C++11, it's just that we haven't evolved to the point where parallelism is really part of it yet.
Well, thank you very much for those questions as well. I want to make sure we use our last moment to ask each of you, we have a room full of people who are going to be getting on a plane and going back home, and they will have time to think about what do you want us to take away and think about for concurrency and parallelism in a sentence each. They're thinking concurrently or in parallel.
Actually, I'm starving.
Are you a philosopher by any chance?
I'm not dining, I can tell you that.
All right. I'm going to say it again. You're going to need to think about parallel task decomposition. With the tools that we're going to give you, that is going to be your next big challenge.
I would say, I would think about how abstract can I phrase the problem I'm trying to solve, and on Monday I'd sit down and try to solve it purely with the standard algorithms library.
I would say don't get overwhelmed by the different directions that things are going in right now. Choose one of the tools that are currently available, whether it's TBB or CUDA or and the implementation of the standard algorithms that are available now, and see if you can make headway towards solving your problems with that. Especially if you don't have a critical problem right now, if you just want to be ready, start learning that by just picking one of those directions and learning about it. Because it transfers, the stuff will transfer.
And I would also say, be more vocal. What are the things that are hard to do? Let us know. Because the problems that we are solving are very, very different from the problems that people in the field are solving, right? So we really want to understand where the pain points are, how can we address that, and then we can also use that as a kind of to reinforce our arguments when we go and present our proposals to the standard committee.
How to reconcile asynchrony and RAII, and to in particular, think about std async, std future, destructor, and std thread, and see how they behave with respect to RAII.
So I would say don't overthink things from the get-go. Temptation is to go and start working with threads and mutexes and all this at a very low level. I would look at a higher level of abstraction to start with, like the PPL or threading building blocks. And if that doesn't give you the performance you want, then you can go and have at it. You'll probably be happier that way.
Great. Well, thank you very much, everyone on the panel. Thank you all for your questions. We appreciate very much what you've shared with us. Thank you.